popped another one into this particular pocket computer, and it started working. And because this plugs into a pocket computer, it is really difficult to try to work on because you basically have to have the whole thing assembled to do anything with it. So if I really wanted to like hook up a logic analyzer or something like that, I'm going to have to, find some of these test points on here, figure out what they do, solder some wires to it, try to get all the wires routed out to hook up a logic analyzer, which would be a pain. So what I did is all the digital I/O lines, the address lines, the data lines, those are usually a very high resistance, like 10 or 20 megohms, right? And most of them were, except for this one guy here, which was only about 500 ohms. And, that really pointed out what was wrong. There's 3 chips on this board. There's 2 RAM chips, which you could still probably find from AliExpress or somewhere. And there's a ROM over here under my thumb. Not knowing which chip was bad, since they're all in very close proximity to each other, I pulled the ROM chip because that was the only one I couldn't replace if it was bad, and that was the bad part. So this repair didn't end well. It couldn't be fixed, but at least the problem was figured out. And it was very, very simple. Signature analysis. This is like saying, to the resistance signature testing, this is like saying, hold my beer, right? We're going one step further. It's another power-off testing method where we're plotting the voltage across and the current through the device we're interested in. It uses a simple and easy-to-build circuit, and it finds faults that are going to be like in the output stage of an IC or transistor or something like that. This is what the device looks like. This has been all over for decades in ham radio magazines and electronics magazines, called the Octopus, after the guy that originally invented it, I think back in the 60s. There's a commercial version of this same thing. Compare them to certain things, and it'll tell you if it's a good comparison or not. It's made by Huntron, called the Tracker. It's basically a little oscilloscope with a signal generator built in. This is the very complicated circuit. Don't worry, there won't be a test. Really, it's a couple resistors and some connectors, and oh boy, okay. Sorry about that. I used some pots on here because they were already on this particular piece of perf board, which I recycled, which is a Radio Shack part number 276 something. So it's a vintage circuit board, vintage perf board for vintage repairs. Yeah, so this is the guy right here hooked up to test a diode. And this, sorry, I'm walking in front of the camera, that's not good, or the projector. So the signal generator here is set to output a 60 hertz sine wave at about 5 volts peak to peak. The oscilloscope is set in XY mode. I have inverted the Y channel because it makes more sense to me to have current increasing going up instead of down. It doesn't really matter. If you look for pictures of this online, you'll see people doing it both ways. But with the simplicity of the circuit, the default way is for the Y to go down when the current's increasing. I used a signal generator instead of the original, used a 6.3 volt filament transformer, which is not as easy to find as it was back in the 70s or 80s. And this also keeps the mains voltage away from whatever people want to test. Makes it a little safer. And you can adjust things on the signal generator, like the voltage level, the voltage peak to peak, the DC offset, because you might have some devices that can be damaged if you reverse polarize them or apply too much voltage. So the signal generator gives you a little more control. And what does this box show us? Well, an open circuit is just a flat line. It's not too exciting. Short circuit is a vertical line, also not very exciting. Resistance is an angled line. The steeper the line, the less resistance. A capacitor gives you something more similar to the traditional Lissajous pattern, which some people call a Pringle or a circle or a wave. That's kind of what it shows you. A diode is like this, and this knee right here is when you're overcoming the forward voltage drop and it's starting to conduct. Ah, darn it, wrong button. Let's try this again. All right. This is a Zener diode. You can also see the Zener breakdown voltage. Now this is an actual test on an actual bad part. It's a MOS 6522 CIA testing port B pins. This is a good pin. You notice it kind of looks like a Zener diode here. It's got a peak going in both directions. This is a bad pin. Now this particular bad pin drove a buffer IC which drove the stepper motor which moves the head. And so having to turn the drive on and off to reset it each time to test every pin involved with moving the head was a pain in the butt. Once you have an idea of where to look, a little tester like this can save you some time. Depending on where you're testing on the circuit board, you're going to have multiple components hooked together. You'll get a convolved signal, which just means lots of stuff mixed up. This was off the base of a transistor, so you see it looks a little bit like our Zener diode with a capacitor thrown in. So it doesn't really matter what the shape is, just that you have something to compare it to. A short sniffer. Oh, one thing, let me back up here. Some things this can be really handy for is, like I said, when it's kind of hard to get something into a state where you can test it. You know, trying to get outputs pins to twiddle, things like that can be a little difficult sometimes. And also where you have a regular diode that's starting to break down and act like a Zener diode in a power supply, that can be a little difficult to test other ways, especially in circuit. A short sniffer. How many people have ever had a short on the 5-volt bus on something you're working on, right? You've got tantalum capacitors. They short out. Sometimes they turn brown. Sometimes they pop like popcorn. Sometimes they don't. And what we want to avoid is using the magic smoke method. We don't want to crank up the voltage and current until something blows, like the traces, and figure out where the short is. So, and this is another really simple device that you can make. That's what this guy is right here. If you have a bench power supply that'll do constant current mode, you can use your bench power supply. It's nothing fancy. I've got a circuit board here which has a short on the 5-volt rail, and I'm using a typical 3.5-digit ohm meter here to try to find it. But the thing is, I'm measuring 0.3 volts there, and just about everywhere. It can be really hard to locate a short because you don't have enough resolution on the meter. It depends a lot on your probes, how hard you're poking your probe into what you're poking into. If you're on an IC pin versus the pad of the IC, there's a lot that comes into play with measuring low resistances. Now we're using the little magic box, and this extra clip here is important. That's what's hooked to this box. And we're in voltage mode now, millivolts. We're measuring millivolts. So we've got 9 millivolts. That's the same place where we started before measuring resistance. 11.2 millivolts there. We went the wrong way. Lower millivolts equals less resistance equals we're closer to the short. And here we're at 4.9. We're getting closer. And notice where we're at. We're on this power pin, the 5-volt pin of this 7400 series logic IC right there. And right beside it, if I can get out of the way, on the bypass cap for that same chip is where our short is. So we had almost 2 millivolts difference between there, and we could see that very easily with this, where we couldn't see it before with a regular ohm meter. So we're able to find the short. It's working like a high current ohm meter. This box is set up to output about 100 milliamps, which is a lot more than a typical ohm meter is going to output. It's based on this paper by Bob Knuckles. The link is right there. Now, a fancy ohm meter is likely to have a 4-wire ohms measurement like this. This one does. I don't have the proper 4-wire lead set for it. But basically, that's kind of what we're replicating with our little box. We're just using a lot more current, which is handy in some cases. This is the basic idea here. I'll try not to step in front of the camera this time. I like to move around. Okay, get out of everybody's way. So the idea here is we have a current source. That's what our little box is providing. and we're measuring the voltage across the device under test. And by using, Ohm's law, we can figure out what the resistance is. So we're basically doing the same thing that our fancy 4-wire measurement on our ohm meter did. And the reason we want to use 4 wires here is because if we were measuring the voltage back here, we're going to be measuring any voltage drop or resistance across the source wires for the current. We want to get those as close to the measuring point as possible to eliminate those. So this is a circuit, super, super simple. It's an LM317 voltage regulator, 12 ohm resistor that makes it a constant current source, about 100 milliamps. And I just clipped the leads right to my, go back, doggone it. Man, sorry, I can't work the technology. Oh man, all right. It's the first presentation, so. We'll do a quick review. Okay, here we go. Now we're in the right section. Oh. Okay. I'm pressing the, okay, here we go. All right. So I'm just clipping the clip lead right onto my meter probe. That's not quite as good a way to do it. It's not quite as accurate, but it's good enough for what we're doing here. We're not worried about an exact ohm measurement. We're worried about tracking down a short. This is a really nice, fast, easy way to do it. Infrared camera. Nifty, nifty device. Very handy for some situations. Easy to get misled by what it's showing you. I'll point this out a couple times. The colorization it does is relative to the delta T, the difference in temperature across the image. So something white hot on the screen does not mean it's really white hot in reality, and it doesn't mean it's bad. And a hot part may not be a bad part. It may be driving a bad part, so it's the one heating up. It just gives you another piece of information. This is a non-repairable, according to Epson, keyboard from an HX20. And I located a short between a couple of columns in the keyboard matrix, but this is made with a double-sided circuit board plus a carbon printed mylar membrane, which is all heat staked together. You can see all these little black bumps on here. Those are all heat stakes. And the membrane is also double-sided stuck to the thing. So trying to get it apart to look any further was impossible. I borrowed an infrared camera from work and ran about 30 milliamps through the short, which was, at a few volts. There wasn't a lot of power being dissipated here. But even with that little bit of power, there was actually a couple shorts here on around two different keys, showed up quite brightly. And the whole delta T in this picture is only 6 degrees C, so don't be confused that that's bright white. If I'd done a better job of blacking out behind it, there would have been less delta T across that, and it would have showed up a little sooner. I was able to fix this. It ran for about a week. I sent it back to the owner, and it quit again because there was a break in the membrane. But it was an interesting experiment. Now, the camera I borrowed from work, I work at a university. It's this FLIR. It's a laboratory camera. It was really expensive when they bought it. It was nice of them to loan it to me. It has a video output and yada yada. It's great. These days, there's a lot more hobbyist-friendly options that are actually pretty decent. Great tool, used in the right application, tracking down ICs that might be bad, things like that. Just don't get misled that warm things are not always bad things. I see that a lot. People are like, oh my gosh, that chip is hot. Well, okay, but that's relative, right? What's it designed to run at and that type of thing. a no-op generator. This is okay, I'll keep going. So we're getting into an area where we're trying to get the computer to help us diagnose itself. And a no-op generator is one of the simplest devices for doing this. It is also the one of the most handy because it depends on the least amount of stuff working to be useful. And all it does is force the processor to do nothing, which doesn't sound that useful. And the fact that there is an instruction in the processor to do nothing tells you how useful a do nothing instruction actually is. You know, when you're writing code that's used a lot of times to get timing just right, or when you were writing code by hand with a machine language monitor, you could use it to fill in areas as you were changing code because you weren't going to reassemble the whole thing by hand. So what does it do? Well, it grabs the no-op instruction and says, oh, I need to do nothing. It increments the program counter, right? Your address lines go up by 1 count, and you grab another no-op instruction, and it keeps doing that over and over and over again. What that gives you is a constantly incrementing address lines, which lets you test lots of things on the board. Frank, IZ8DWF, did a very good video on this, talking about a lot of the complications of trying to do this. Here he shows the schematic for a Z80 of the pins that you need to tie low and high to make it think that it's reading a no-op instruction all the time. Anytime you're pulling a pin high, you want to do that through a current limiting resistor. Don't just tie it to 5 volts. So making one of these for a lot of processor systems is not terribly difficult. You're just clipping some pins on a socket and you're plugging your processor into the top of the socket, and you plug this into your circuit board. And now that your address lines are all twiddling, you can measure them with a logic probe or a scope. You make sure they're twiddling, they're going to the right voltage levels, that all your address decoding and your chip selects are working when they should work. This can let you track down a lot of problems on a machine that's otherwise not wanting to work very well and being cranky. And it's really simple in most cases. For instance, for testing out a processor you're not that sure about, a very handy way to do it, that's what I was doing here with an RCA 1802. It just gives you a basic idea that it's doing something, it's not completely dead. Go back one. Where this is difficult are processors that have multiplexed buses, like the 8085 and the Model 100. That's rather difficult. 65H16, anything like that with a multiplexed bus, it's hard to get this done. The MOS 6510, it has some extra bits in it to do memory banking, so that can get in the way of trying to do something like this. Diagnostic ROMs. This is like the next step up from a no-op generator. Very, very useful. Some of them will have a diagnostic board that goes along with it or in addition to it, that type of thing. Having a diagnostic ROM that you can plug in is a little better sometimes than having a diagnostic program, because with the program you got to have more of the computer working so you can boot up the computer enough to load that program in by whatever means. With a ROM that you can plug into the board in case of the factory ROM, you don't have to do that. And these are tricky programs to try and write, because what happens is the computer boots up, you assume it's not working, you don't know if you have any RAM working whatsoever, so therefore your program cannot make use of any RAM. You can't do anything that does loops, because that requires the stack, which you can't guarantee that it's going to work. So you have to write the code in a very linear fashion, and the first thing you do is test the RAM, and if you find a block of RAM that's good, on a processor like the Z80, you can say, okay, now put the stack there, and you can switch into a different testing mode. If you're on a processor like a 6502, you can't do that because the stack lives at one place. And if that RAM isn't working, you're stuck. You can't do anything else like this. Anybody ever seen one of these in real life? Model 3.4 diagnostic board. This would accompany the diagnostic program that you can download now, the Radio Shack diagnostics program. And it plugged into the 50-pin connector on the back and did some automated test of different I/O. I heard a rumor that somebody was going to respin this board, which would be kind of fun. Ian is waving his hand back there. Yay! Okay, that would be nifty. Because when you're working on a machine, especially if I'm working on a machine for somebody else, I want to test everything I can test before sending it back to them. Because the worst thing in the world would be that they get it and they were like, oh, I'm going to plug in a printer or something and that doesn't work. Or I'm going to plug in a modem to the serial port and that doesn't work because, you know, one of the handshaking signals isn't quite right. Some computers like this 4P right here, which is actually on the table over there. I got this at the show last year and got it working. Running back here is the memory test program that's part of the 4P ROM. You hold down some key, which I don't remember what it is right now. Yeah, when you're booting, and it'll test the first 64K bank of RAM for you, which is handy, and it was flagging an error, and you can't quite see what address it was back here. But that was enough information. You know, it was saying, I'm writing this and I'm reading this. And that was enough information to say, oh, this has a stuck bit, right? So odds are that's a RAM chip. But you also have, buffer chips on, you know, bus latches on both sides, input and output of that system. So it could also be one of those bus latches not working right. Yeah, all it took with that information and knowing which bit it was my period correct Radio Shack logic probe. I bought this, I bought this guy in Marysville, Ohio in the 1980s when I was in high school. That's the only tool it took with the built-in RAM test that was part of the ROM to track it down to figure out it was most likely the RAM. I swapped it with a chip in another position since they are all socketed, and that confirmed it. A very, very handy thing. Can save you a lot of time. Another type of system here, this is a Model 100 board. This back here is a test harness. A friend of mine designed this with a PCB in this area. This plugs into the ROM socket. It's got an EEPROM on here, and he memory mapped a little LCD screen in here, which was the most brilliant thing in the world because this will give you visual confirmation about what it's doing and what it's finding without the system LCD even having to work. You don't have to get that far to know what's going on. Later on, he made a loopback cable for the keyboard right here, so it outputs, you know, one side and puts the other, so you can test those signals, and made a loopback board for the LCD that not only tells you have the correct system voltages, but it'll test that all the control signals are there. Pretty nifty stuff. And this is the memory mapped LCD. This is right after it's done the second RAM test. And this basically means, and you have to read the manual that he wrote for it to understand what all this means. This means that all 4 RAM modules are good. If one of them's bad, you'll get some other feedback in here. And the RAM test on this is so good, it'll tell you which address line it's having a problem with. You can look up the alphanumeric code here and figure that out. It's pretty awesome. It saves a lot of time. You guys probably seen Adrian? Yep. He's recently been working with a couple friends doing some diagnostic ROMs for the Model 1 through 3, which is great. It kind of does a lot of the things we've been talking about here. It starts out doing a RAM test, testing the screen. You know, it finds, when it does the RAM test, it finds where to stick the stack, everything like that. It's going to be a big time saver. You know, it's nice on the Model 4P. I had that built into the ROM, but these other machines don't, so this is great. The next step up from a diagnostic ROM is what I've kind of lumped into this processor RAM/ROM emulator. There are true microprocessor emulators, which is a box that acts like the actual processor and lets you set breakpoints and things like that. They're used a lot back in the day, very expensive devices. Today we have devices that sit between the processor and the system, which will intercept calls to the RAM and ROM in certain address ranges that you set up and let you see what's going on. So you can load diagnostic code into this emulator device instead of having it on a separate ROM, that type of thing. Some things will allow you to set fake breakpoints where basically they just keep running a no-op at a certain address location. And I think, somebody correct me if I'm wrong, nope, it's on the next page. I think Arno was showing that Pocketress was doing that in some extent last year, being able to set breakpoints and run no-ops and everything like that when he had that mapped and plugged into a computer mapped into a unused address range. Some of the commercial options are the Fluke 918A. This is a vintage device. People love this thing. Guys who do repair vintage arcade boards, things like that. The ROMulator is a newer one that's very similar. I think Arno may have done some more work on the Pocketress in this way, but I don't know for sure. This is the 9010A. It's kind of a funky little device. There is a separate board which they call a pod. So you have a pod for a Z80, you have a pod for 6502, you have a pod for a 6809, right? That plugs into place of the processor. And it helps you intercept these things. You can punch the right keys on here and set outputs and things like that, see what's going on, check the content of RAM, that type of thing. The ROMulator is a more modern version of that. It's got a little FPGA here on the board, and you plug this into your CPU socket, and you plug your CPU into here. And there is some software where this thing on certain machines will even visualize the screen remotely for you. So if your screen's not working, you can still see what's going on. You can like interrogate memory, because this thing can map its own memory in place of the system memory in a lot of cases. So it gives you a visualization of what's happening. Go back one more. The downside to these things is they're a lot more complicated to use. It's a lot more involved getting one set up and running and interpreting the results than using a diagnostic ROM. But they can be very helpful in some cases. My friend that did the Model 100 board, the diagnostic board, made something like this for the 8085 because of the multiplexed address and data bus that basically was made just to interpret what the 8085 was doing so he could set breakpoints and see what was going on because it was doing something very silly. Now this is more equipment related. A logic analyzer. I think there's actually a logic analyzer I saw over here. Okay. Yep. This is going to be similar to one I have a picture of, which is just coincidental. It's a visualization device. It lets you see multiple digital signals at once. It's awesome. It'll do a lot. It can be very time consuming to use, time consuming to set up, hard to interpret all the data that it's giving you because it is a lot of data. It doesn't find analog problems. The problem I was talking about before where the Model 100 diagnostic board told me there was an address line problem, it said address line 10 was bad, right? And I looked at that on the scope and I had this slope like this, very characteristic capacitor discharge type curve. Well, what the logic analyzer is going to show you is that the edge of that signal was in the wrong place, right? But you're not going to see that slope. It's going to mask it, and it might make it harder to figure out what's going on. It does let you see multiple things at once, though. So this is an old classic, an HP 1664A. I don't know if that's what that one over there is, but it's very similar. Notice the 3.5-inch drive. Very important, if you want one of these vintage units, you see this bundle of wires up here that's got all the leads. Super, super important because where this plugs in down here, these are unique connectors. This whole cable is, you can't replicate it today. So it's very important you get the cables with it. These had a lot of functionality. They could understand the like different serial protocols. You could get basically additional software that would let it understand different bus architectures for different processors. So it could help you to decode what it was seeing on an address or data bus. Very handy. Their biggest drawback is, they're not too expensive today. A couple $100 on eBay for one that is working but not guaranteed. But they're kind of big and kind of noisy. This is this little black box right here. This is an original Saley Logic 8. It's only 8 channels. I bought it like 15 years ago for $100, which is really cheap then. It's PC based. The software they output at the time was awesome. It's still awesome today. The biggest drawback of this guy is that it's only 8 channels. They used an off-the-shelf USB to parallel I/O chip, and it didn't take too long for the clone mills in Asia to figure that out and start putting these out for 15 bucks. And you can still get these 8 and 16 channel clones for that amount. So what they did is they upped their game, and all their devices now, they're a similar size, a little bigger, more channels, and it's like a mixed signal type of thing. So it has some analog capabilities as well as the digital. So here, what I'm looking at is a Tandy PC4. I've got actually this unit back there on the table. And this is a little PIC processor back here, which is pretending to be a 1K RAM expansion. So I've got a processor that is way more powerful than the whole pocket computer acting like RAM. But this unit was made by Casio. It used a weird RAM chip. It was a 4-bit RAM chip with a weird protocol, and the whole Casio bus is on that same thing. So hooking up a logic analyzer. This is a Model 100 board. I've got a dip test clip, which these are handy. You can find them on eBay. Super handy in different sizes for different chips. Hook up the leads with a logic analyzer to do that. To get, I was looking at the data bus here, but only D0 through D6 because there's only 8 channels, and I needed to look at the read signal to have a timing indication to know when to look at the data, when the data was valid, because I was trying to capture everything being read from the EEPROM to figure out why this wasn't booting up. And this is the output of that. And I just use, you can actually write scripts in this so it can understand different protocols. This it has a built-in what they call simple parallel decoder, and I just said, hey, address line 7 is my timing signal. And so it kind of automatically crunched everything down so I could see what was going on and see the opcodes. But since I was missing bit 7, I had to guess at what it was and what opcode was really running. But there's annotated, ROM disassembly, so it wasn't that hard. And then I could, after capturing what was going on, following the opcodes that it was running and going through the ROM disassembly, I could see where it was failing. And it turned out to be a RAM module. It was overwriting the stack. As it was trying to copy some code from ROM into RAM, and that was overwriting the stack. And then when it tried to return, of course, it went to La La Land. And that was a very time-consuming repair because it was the first Model 100 I ever worked on, and having to go through this method. And my friend's little diagnostic board now would find this in 10 seconds. But the logic analyzer is far more versatile. It just can be a lot more time-consuming. So what do you do when you get to the point where you've used the tools and the techniques and you think you've got a bad chip? There are various chip testers out on the market, which can be very handy. And there is also a thing made back in the day called a logic comparator, which we'll talk about toward the end here. The first things are out-of-circuit chip testers. You desolder your chip, or you pull it out of the socket. You plop it into this thing. This is one people seem to like a lot. It understands a lot of common chips, 7400 series chips, RAM chips, things like that. You plop it in here, tell it what chip that you're testing, and it'll tell you if the chip's good or bad. All of these things have limitations. You could have a chip that will work great at low speeds. When it's actually in your computer, it'll fail at high speeds. The bad RAM module with the A10 line that I was telling you about, that actually worked on this guy that I made. It tested fine here, but would fail in circuit because, I'm driving this with an Arduino, which has a much more powerful outputs, right, than the chips in the Model 100 have. It also has a lot better capacitive loading capabilities than, all the stuff is already on the bus in the Model 100. So that chip tested fine here, whereas it failed in circuit. So you can get some deceiving results. You can have a chip that kind of works right, but it's drawing too much current. The chip tester, there's some chip testers which will tell you, it'll know about how much current the chip should draw, and it'll tell you if it's too much. You might have a chip that's not able to output enough current from a particular output that might fail. So these are handy. They're not foolproof. You can make these type of things yourself. This was a RAM tester I built with an Arduino Mega, and then I turned it into a tester to test the Model 100 modules because I was repairing some of those. And I just made it so it would tell me which chip, there's 4 chips on the module, which chip was bad. And the DC to DC converters were here, so I could like test 416s and everything, which have multiple voltage rails. The HP logic comparator. This is quite an interesting device that HP made back in the day. You attach this clip here to the chip that you want to test. These boards that are standing up here in the background are like personality modules. These are wired, so you tell it which pins on the chip you're testing are inputs and which are outputs. You plug in a known good chip of the same type into this board. This board plugs into here, and any differences in the outputs, it'll light up an LED right here. So you can do live in-circuit testing, and it doesn't really need to know how the chip operates, just which pins are inputs and which are outputs. It's limited on pin count, but you can think about a computer from like the late 70s, early 70s with hundreds of chips on it. Yeah, that could be handy, not having to pull them all out if you think you might have a bunch of RAM chips failing, something like that. Again, not foolproof because you're clipping, this lead, this big lead on something. You're loading down the circuit a little more, which might be problematic, that type of thing. But it can be handy. There is a guy in England, Jerry Walker, that made a modern version of this. That is actually a 40-pin tester, and he sells the boards for that. So this is something I haven't got into. I think it's a pretty neat idea. And if you think about this Arduino Mega type of thing here, if you design a chip tester around this, you're saying this is out, sending outputs to the inputs of the chip you're testing and reading the outputs. So it needs to know how the chip operates. Whereas this guy doesn't, but it's a little more limited. But you could take your Arduino and make an in-circuit chip tester kind of the same way. It just needs to monitor the inputs and the outputs to the chip you're testing and know how they should match. And then you could make your own in-circuit chip tester. It'd be an interesting project to do. Conclusion. The basic skills are by far your most useful set of tools. Everything the fancier tools and equipment tell you, you wind up relying back on that earlier stuff. They can give you a lot of time and insight. The diagnostic ROMs and test harnesses and things like that can save you an awful lot of time in certain situations. They can also lead you astray. I've been very guilty of that on the Model 100 because I've got the test harness. I'll plug it in. And I can remember one time I was working on a 102 that I worked on it for hours and gave up, and a couple days later I sat back down and I just started from basics, right? And the problem was I had measured for signals at the RAM, but not at the ROM. And there was a break in one line going between the RAM and the ROM because some corrosion from the battery pack at some point in decades past happened to one little crumb, fell in a certain area and corroded one trace. And so even with the fancy tools, that's not going to do it for you. It's not going to tell you what's wrong. It's kind of like the check engine light on your car, right? And you take it to the garage and they plug the scanner in there. When my daughter went to university, she was away from home, and check engine light came on in her car, and I said, well, take it to the auto parts store. They'll scan it for you for free. And she calls us. She said, well, they said the transmission's bad, but that doesn't make sense. She said, but here's the code. And the code was that there was a mismatch between what gear the transmission thought it was in and the gear selector on the tunnel. So there was a separate set of switches in there that lit up the LEDs on the dash to tell you what, if you had an impart or reverse or whatever. And that didn't match what the transmission was doing. And so, the powertrain control was going, yeah, there's something, not right here. But, the guy at the parts store said it's a transmission code, you need a new transmission, right? And, and the problem was the switch was sticky. It could have had a soda spilled in there. It could have just been, it was an old car, that type of thing. So the fancy tools, scanners, all this stuff is great. But it can't tell you how to fix your computer. Questions? Yeah.
What do you set the current at when you do that?
About 100 milliamps.
100 milliamps.
Yep, that's usually nice and safe for most stuff. And you want to set the voltage to something that's safe for the system you're working on. This box has 3 AA batteries, so output about 4.5 volts,
Okay.
which is safe for, like most of the older stuff we're working on, the 5-volt systems. So your bench power supply, set it,
Constant current,
right.
not voltage, not too high, and then just set
Yeah,
it
just set it for 5 volts, 100 milliamp, current limit, and it'll work great. I had these boxes left over from an old project, which was putting a bunch of LEDs on a guy's Christmas ornaments because he really loved them. So I think I have like a dozen of these. If you want one of these 3-cell boxes, it has a switch that goes, power on and blink. I just scraped the little chip blob thing off of there and wired it so it was on all the time. But I'll give those to anyone that wants one because they've just been left over. But yeah, I don't think I mentioned when talking about that, the higher current helps out a lot of times when testing things like switches and contacts and things that may ohm out, okay, because you're not putting much current through it. Years ago, I used to work on very high current devices like welding power supplies where you might have 100 to 600 amps, right? And you couldn't tell, you could ohm out a cable and it would ohm out just fine, but it sure would not carry 600 amps, right? Because you could have just a handful of strands of wire in that cable being good. So load testing it, pushing more current through it was the only way to really tell that it was okay. Yeah, if the thermal camera probably would have seen that there was a spot in there with high resistance and it was getting hot. So that's another good use for that.
I'll ask another one because it's short. So I'm really excited about it. What's the trade-off between using the constant current and looking for the voltage changes versus using the thermal camera? What kind of makes you go with one or the other when you're figuring out what's shorted out?
In this case, there's not enough current going through. Well, with this type of testing,
Yeah.
you're not powered up, right? So it's not like the machine's running, but it's not running right, and some chips are getting hot, right? That's one use case. A thermal camera might be great in that situation, right? If it won't turn on at all because it keeps blowing fuses because there's something shorted on the board, right? Or you're switching, the switching power supply will normally just shut itself right back off, right? And don't put on a bigger power supply in that case, right? Because you'll vaporize something on the board. So yeah, this is a good power off method.
Well, a lot of times we see the driver voltage regulator going to the thermal shutdown because something else is shorted, and you've got a false positive off the clear telling you that they think the voltage regulator is
Right,
bad.
right, exactly.
Below the voltage regulator is trying to drive.
Yes, yeah. So the hot thing isn't necessarily the bad thing.
And most of the time it's a decoupling cap or a tantalum.
Yep. Yeah, that's a very common failure mode of a tantalum is shorting. Sometimes they'll turn brown and tell you. Sometimes they'll blow up and tell you. Sometimes they just sit there and look perfectly normal. Any other questions?